So this screencast will look at the law of conservation of matter, and we will examine what all of this means, what the definition of the law of conservation of matter means. And in addition, the law will be demonstrated using molecular model kits. In addition to understanding the law of conservation of matter a little more deeply, students will also hopefully gain a deeper understanding of the three-dimensional nature of molecules. And last, we will also introduce the law of conservation of energy through looking at the processes of photosynthesis and respiration. So first, let's start with the definition of the law of conservation of matter. I'll give you the overall statement and then we'll walk through it. So the law states that matter cannot be created or destroyed in any physical or chemical reaction. It can only change form. So let's start with the definitions of each part of this title. Law. Law in science is a step above. It means that this law has been studied and experimented upon in many different ways by many scientists. And the essence of the law will not change. It's not expected to be changed. It might be tweaked a tiny bit, but the law is withheld. Conservation means holding or conserving the amount of anything. So in this case, it's the amount of matter. So matter won't be created or destroyed. It will be conserved. There will be the same amount no matter what happens. Now let's look for the definition of matter. As you can recall from lecture, matter has mass and occupies space. And the basic unit of matter is the atom. Atoms consist of three main units and other subunits. The two units in the nucleus, or the core of the atom, are protons, which are positively charged, neutrons, which are neutrally charged or not charged, and then spinning in orbit around the core of protons and neutrons are electrons. So in a particular atom, the most mass and the most occupied space will be in the nucleus of the atom with the protons and neutrons. And electrons do contribute, but are much tinier in mass and space. For our purposes in this screencast, the important number that you need to know is the number of protons, and that's also known as the atomic number. So next we'll look at how this concept of having an atom translates into being an element. So you see this example, which we have is carbon, and it has 6 protons in its nucleus, or an atomic number of 6. Whenever you have an atom with 6 protons in the nucleus, or an atomic number of 6, that atom is the element carbon. If you have an atom that has 1 proton in its nucleus, or an atomic number of 1, that atom is hydrogen. And if you have an atom which has an atomic number of 8, or 8 protons in the nucleus, then that atom is oxygen. So that defines what it is, how it will behave, and it's given a name, an elemental name, based on the number of protons. So let's look at the periodic table of these elements. The 3 elements that we are going to look at today include carbon, which is written with a capital C, which contains 6 protons, oxygen with an atomic number of 8, which contains 8 protons, and hydrogen with an atomic number of 1, which has 1 proton. Now, it can be a little confusing. Here we are talking about a single element. Sometimes molecules, which we will address in the next screen, sometimes molecules have the same name as the element. So for instance, the oxygen that we breathe in is a molecule made of 2 oxygen atoms. So that can be a little confusing, but just keep in mind that that's how it can work. Okay, now the definition of a molecule. A molecule is 2 or more atoms bonded together. the atoms that make up a molecule might be identical. So in this case, O2 is the oxygen molecule, the oxygen we breathe, and it's made of 2 oxygen atoms. Some molecules are made of a mixture of different elements or atoms. So in the case of water, or H2O, there are 2 hydrogen atoms and 1 oxygen atom all bound together. So notice the number of atoms is noted or denoted with a lowercase or subtext number. When there's no number listed, as in the case of the oxygen and water, that number is 1. So the last example is carbon dioxide. This molecule has 1 carbon and 2 oxygen atoms in it. Okay, now we move up to the next level in that when we write equations that represent chemical reactions, there are often multiple molecules involved. So it may not be 1 oxygen, 1 water, 1 carbon dioxide. So the number of molecules that are either the reactants, the part that's going to go into a chemical reaction, or the products might be any number, 1, 6, 10, okay, could be any number, and that number of molecules is written with a full-size number. And if there's no full-size number written here, then it's simply 1 molecule of that particular molecule. Okay, at the beginning of the definitions, let's go back to that real quick. We had matter cannot be created or destroyed in any physical or chemical reaction. It can only change form. So next we're going to look at what a physical reaction is, what a chemical reaction is, and then we'll look at how it can change form. So at the top here is the physical reaction, and molecules here are rearranged, but they're not changed. So the classic example is aluminum foil. If you rip the aluminum foil in half, you haven't lost any atoms of aluminum. You haven't gained any atoms of aluminum. You simply split them apart. You physically separated them. And a chemical reaction is quite a bit different than that. In a chemical reaction, the atoms that are on the one side of this equation here, the reactants, actually break apart from one another and recombine with other atoms to form new molecules. The example we'll use is photosynthesis. In that case, we have 6 molecules of carbon dioxide and 6 molecules of water. In the presence of sunlight, these recombine, so you get 1 molecule of glucose, so there's no number in front of the molecule, but it has 6 carbon atoms, 12 hydrogen atoms, 6 oxygen atoms, and you also get 6 oxygen molecules as well. So let's look at what happens. That's our example. This is how the chemical formula for photosynthesis is written, with reactants on one side and products on the other side. And during this reaction, both mass and energy are conserved. So that means if we start with 6 carbon atoms here, 6 times 1, then we're going to have 6 carbon atoms on the product side. If we start with 12 oxygen atoms, 6 times the 2, hydrogen atoms, 6 times the 2 is 12. And here we have the only 12 hydrogen atoms. Now the oxygens are going to come from 2 different molecules. So we have 12 oxygens here and 6 oxygens here, making 18 oxygens on the reactant side. And here we have 6 times 2 or 12 plus 6 is 18 oxygens on the product side. So here are your directions. You will need a flat, stable work surface, such as a desk or a table, and you need 2 miniature molecular model kits, which were included in your EMV 118 lab in a box. And the kits come in these little bags, and you'll see a yellow insert. you'll see various color pieces, blue, purple, red, orange, white, whatever. So you'll need to have those, and if you want to have any paper to make note in addition, you can certainly have that. So you have 2 bags, and I'd like you to set one aside, and then carefully empty the other bag onto the work surface, making sure that the pieces don't go bouncing off of your work surface, and retrieve them if they do. And the atoms that we are going to need are oxygen, carbon, and hydrogen. And you can tell on your key that's written on the yellow paper here. The red pieces represent oxygen atoms. So you'll see a little red piece. It looks like a little red plastic circle, and it has 2 prongs on it. And the black pieces represent carbon. And again, that looks like a little carbon, let me try to get this one off here, a little carbon ball with 4 prongs on that. And then the white plastic piece, the little plastic hard piece that's not bendable, represents the hydrogen atom, and it has 1 prong where it can bind with other atoms. The white tubes represent the bonds between the different atoms of the molecule. And I'll show you those in a picture in just a minute, but what you're going to do is assemble the atoms needed for 6 carbon dioxide molecules and 6 water molecules. To do that, you will need to borrow 4 red atoms from the second bag, but that's all you'll need from the second bag. So here is an empty bag, and these long things are the tubes that represent the bonds. There's a hydrogen, there is an oxygen, and there's a carbon. And you are going to assemble the reactants here, 6 carbon dioxide molecules, by placing down 6 black carbon atoms and placing on either side of them 2 oxygen atoms for each. And for the water side, you'll need 6 oxygen atoms making the core of the structure, and you'll need 2 hydrogen atoms, or the little white pieces, sitting on either side. Then you'll take the tubules that represent the bonds and put together or connect the, in this case for the water, the red oxygen atoms with the 2 hydrogen atoms. And you'll get a shape such as this. So it's not a straight across, it's actually angled. And these molecular model kits show you the angle. Water has a single bond here between its atoms, and so you just have 1 tube connecting each. When you're ready, you can pause this screencast, and when you're ready, go on to make the CO2. The CO2 requires double bonds, which means you will need 2 of those white tubes to attach to one of the oxygens and 2 of the white tubes to attach to the other oxygen. And it doesn't matter which sprocket you are attaching the tubes to. No matter how you do it, it will always end up in this type of shape. So again, you can pause and make this these sets of reactants. So when you have completed building your models, take a note again of the single bonds over here and the double bonds over here. Take a note of the 3-dimensional structures here, that everything's not just going across in a straight line. And you have now assembled the reactants for the process of photosynthesis. In the next screen, I'm going to show you the reaction of photosynthesis, and then we will start a new screencast. So here's photosynthesis. The sunlight energy comes in, and all of these atoms and all of these bonds come apart. And I want you to do the same thing. Disassemble them completely, and then you're going to go on to build the next part, or to rebuild or reassemble the glucose and the oxygen.